Good evening, friends. Welcome to the Tatarskii Memorial Lecture today, uh, organized by the Indian Radio Science Society. We are extremely thankful to Dr. Saba Mudaliar, who has kindly agreed to give this Tatarskii Memorial Lecture. But before we get started, I'd request the President, Indian Radio Science Society, Professor S. Ananthakrishnan, to say a few words of welcome. Professor Ananthakrishnan.
Yeah, thank you, Eva. First of all, a hearty welcome to Dr. Saba Mudaliar for agreeing to give this talk. Saba comes with a very highly recognized by the U.S. National Committee for RC, and he has been chairing many conferences on wave propagation in random media and Tatarski's work and all that. I think he is probably even editing a book on the same subject. Now, Tatarskii was a very great man, and I have heard him from my college days, and we used to be in awe of him. And it was all because everything that he dealt with was wave propagation in turbulent media. And turbulence has, of course, a very large effect on wave propagation. And it can be described by only complicated differential equations. And then, of course, it all starts from Maxwell's equations, I suppose. And then there are all kinds of approximations and whatnot. And then, of course, from these, one finds amplitude and phase variances. And from these variances, again, one builds up a whole theory, and you get the power spectral density of the waves, and you can find the beam profiles, and so on and so forth. And you can find strong ratio, and so there are a variety of things. I used to be sort of scared of dealing with Tatarskii, but I hope that Saba makes it easier for all of us to understand. Even over the years, I have not managed to pick up all of that. I use the minimal equations that are required from that great work of Tatarskii, and it's a great honor for the Indian Radio Science Society to be able to arrange a Tatarskii Memorial Lecture, to which our governing board agreed very heartily. And that is how this lecture has come to pass. So I again welcome Dr. Saba Mudaliar for agreeing to give us a talk. Thank you.
Thank you, Professor Ananthakrishnan. Professor Animesh Moitra, would you like to say a few words? Hey, Animesh, you are muted. Not yet. You are still muted, Animesh. Animesh, you are still muted.
Maybe somebody sent a chat message to him so that he can see.
Oh, well, perhaps he can hear us, but he is not able to unmute himself. Well, okay, Animesh, let's do this. Maybe you can, after the talk, you can say a few words. Well, it's.
Can you hear me now? Yes.
Yeah, okay.
Yeah,
I could manage.
Please go ahead.
I was just out of the screen, that's why. Okay, now this is a very important topic about we're talking on, and particularly this has interest to me. Now, I would just would like to mention a few historical thing about this. Although a lot of theory came up on atmospheric scattering, irregularities, spectra, but I think the first detection of atmospheric irregularities was done in Kolkata, Calcutta. At that time, it was known by Shishir Mitra and his group. In 1930s, Shishir Mitra and his group was experimenting on ionosphere, you know that, and Shishir Mitra worked extensively on D layer and E layer. Now, on some occasions, they got reflection from very low atmospheric region, say 20 kilometers, something like some 20 kilometer like that. And Mitra's group thought that it was some spurious kind of things happening. So first, initially they ignored that, but later they consistently obtained this kind of signature from their ionospheric measurements. So then they become sure that it is certainly something is happening at lower atmosphere below 20 around 20 kilometers. And then he wrote a paper in Science and Culture, initial report they made. And then he made a very brief, published a brief paper in half a page paper, I think, in Nature. And he called that these reflections are coming from C layer. So there, you know that there are D layer, E layer, F layer. Then he called it C layer. Of course, later at that time, Shishimito wrote that he could not explain this, how it is happening, because it is not coming from ionized layered, and then existing magneto-ionic theory could not explain how reflection of wave can occur from such a low height of the atmosphere. Of course, a few years later, others people also discovered or got the signature of this low atmospheric layer. And later, of course, many people explained that, and a new area of atmospheric radar came up in 1970s. But origin was Shishir Mitra's paper in Science and Culture and Nature. So that was the historical. I just like to mention that was the historical origin of atmospheric irregularities, on which Saba is going to talk today. So I don't want to prolong my uh, talk. So this much I wanted to say at this moment, and let us hear from Saba, and then we'll see what we can learn from his talk. Thank you.
Thank you. Thank you very much, Animesh. So let us get started with our talk for the day. Before we get started, I have the pleasant duty of introducing our speaker today. Dr. Saba Mudaliar is a senior researcher at the Sensors Directorate of Air Force Research Laboratory in Dayton, Ohio, in the US. He has extensive experience working on propagation and scattering in statistically modeled environments. For the last 15 years or so, he has been continuously organizing special sessions on random and complex media in IEEE antennas and propagation symposia and ERSI meetings. He is on the editorial board of the journal Waves in Random and Complex Media. He is also a guest editor for the 2023 special issue in honor of VI Tatarskii. So with that brief introduction, may I invite Dr. Saba Mudaliar to give the Tatarskii Memorial Lecture for the Indian Radio Science Society. Saba, the floor is all yours.
Let me share my screen and
Yes, please. All the rest of us will switch off our cameras.
can you see my screen?
Not yet.
No, not yet.
It'll take a few seconds to come up, maybe.
About now.
Yes, yes,
So it's in presentation mode. Yes.
yes, yes.
Okay. Thanks, everybody. Good evening to you all. And first of all, it's a pleasure and honor to give this Tatarskii Memorial Lecture to the Indian Radio Science Society. I have to thank Professor Ananth and Dr. Sengupta to inviting me. And what I'm going to do today is to, as you know, Professor Tatarskii passed away recently, and he was widely regarded as a father of statistical radio physics. We had two memorial sessions last year at the ERSI meetings, and we are working on a special issue to honor his legacy in Waves in Random Media, and this is going to be published early 2023. There is also a nice tribute article that has been published in Radio Science Bulletin. I think which is coming up shortly or has already been published, but I have seen this that article. It's by one of his students, and there are similar tribute events and in other societies as well. For instance, in the Acoustical Society of America had a special tribute for him, and publications for him, and also in the Optical Society of America also had a special tribute for him. So I'm sure there are other societies besides this that has honored him. So this gives you an idea of the breadth of his influence everywhere around the world. So I will, in this talk, I'm going to give you an overview of some of his work and how it connects to recent developments, and show what the path ahead in this area. So we are interested, in this talk, we are radio scientists, and so we are interested in how the radio waves propagate and scatter in an inhomogeneous medium. Okay. So what we do is we start with the, my question is this, what is inhomogeneous medium? I mean, all nature is inhomogeneous. It's only the degree of inhomogeneity that varies, and the yardstick for measuring that degree is the wavelength. Okay, depending on the wavelength, the same medium will be heterogeneous or homogeneous depending on what wavelength you use. So inhomogeneity is everywhere. So it's a question of where, how important and how significant is for your problem. So in our case, the inhomogeneity is in terms of the permittivity fluctuations. And the permittivity fluctuations, to capture that, to represent the permittivity fluctuation that happens in nature in all its spatiotemporal detail is very complicated. So the expedient approach to this problem, and even the desirable approach, is to take a statistical model for this. And this is the permittivity fluctuations. And I hear some background noise. I think somebody has not muted the phone, so I think that might interfere in my talk. So I just want to ask whoever is. So there is some, this is the permittivity fluctuation, and we model it as a random process, okay? So we start with the Maxwell equation in the, this is a time harmonic wave equation for this. And if you assume that the gradient of emittivity is small, as it is shown here, this reduces to a scalar equation, which is a Helmholtz equation. So the main question is that if we have the random process that describes the permittivity, what can we say about the statistical properties of the wave function that governs? There's a size, a wave function. What is the wave function? What is the statistics? That's a very big question and is a difficult one. So we can reduce the scope of this problem by saying that, how do I understand, what do I know about the first two moments of the wave function? That is the scope, the reduced scope that I want to present myself. There is there's a subset of this, of this problem that we can do with much more rigor, and that is the case when the wavelength is much smaller than the scale length of the fluctuations. And when you do that, then there's all the scattering and propagation takes place in the forward direction. And so we use these ansatz. I mean, the forward direction for us is the z direction. So along the propagation is the z direction. So the Helmholtz equation transforms into this form, this equation. And if you assume this, I mean, since k is large, this inequality holds. And we arrive at the following parabolic equation with the following initial condition. This parabolic equation allows us to treat this problem with much more detail and more rigor than the Helmholtz equation. So these are the two frameworks that I will use, the Helmholtz equation framework and the parabolic equation framework, to study this, the wave functions and the statistics. That's what I will do in this talk. So I'm going to give an outline. This is an outline of this talk. And before I do, I'm going to spend a considerable amount of time on this talk. And then, as you can see, there's a list of techniques for dealing with for treating the wave propagation problem in a turbulent environment. So what is it? Why we have so many different approaches? I mean, these are all, it looks like, at first instance, it looks like there's an assortment of techniques just put together. But the fact is that there is no one general technique that applies for all applications. It's a very difficult problem. This is a statistical problem. We are solving SPDE, which is statistical partial differential equation, which doesn't have any known solutions for this unless we restrict our attention to a subset of this. So that is the reason why we have so many different techniques available, and each technique corresponds to a special case, and each special case means that it has a narrow domain of applicability. That's what it is. So, for instance, in the case in the geometrical optics, what we have is the wavelength is much smaller than the scale of fluctuations, and also geometrical optics ignores diffraction. So we have to stay in a regime that is less than the diffraction limit. So we have to stay, the diffraction zone is there, and then that's toward the Rayleigh zone. So we have to stay within that zone, much smaller than that. So this is a very serious restriction on the range that can be used for studying this, using this geometrical optics technique. The radiative transport theory has been there for a much longer time. It's an old theory, and it has it's a wide, it has a much longer range that we can use to study this problem. And it involves, it takes into account very nicely the multiple scattering effects. This is a phenomenological theory. The main foundation of this theory is the conservation of radiance. And it is and then the main quantities that is involved in the equation of radiative transport theory has been traditionally phenomenological, which means that the scattering function and extinction functions are derived from measured quantities. So measured quantities, that's what it is used. So it is data specific. So that's a traditional way this theory has been used for quite some time. One of the main drawback for this is just the fundamental quantity here is radiance, which means that it doesn't have any information about the phase. Information is lost. So the importance of phase information, one might know that In the case of imaging, phase distortion is the main factor that distorts imaging. So the phase information is very important. So in that application, so which is something that this is a shortcoming of radiative transport theory. So what is the tools that we have if I want to treat both amplitude and phase into account? And at the same time, I don't want to restrict myself to the small wavelength case, as in the case of geometrical optics. So what techniques that we have? One approach for us is that we can have some control over the fluctuation, the magnitude of fluctuation. If I treat the magnitude of fluctuations to be very small, then I can seek a perturbation expansion for this problem, and then seek only restrict my attention to the first perturbation expression, and then get solution. That's the approach that has been used in the weak fluctuation. Weak fluctuations corresponds to the case when the fluctuations on the permittivity is small, and I'm going to restrict out my attention only to the first term, the leading term. There are two things here. Then with the Born approximation and rate of the Born approximation is the case when this is for the Helmholtz equation framework. That is when I use the weak fluctuation theory, that's called the Born approximation. And if I use the parabolic equation framework, that approach is called the rate of method. Okay, and this restricting ourselves to the first term places restrictions on the parameter space that I can use for this, with this theory. So that is that means that we are excluding ourselves from treating many practical problems where the fluctuations are not weak. So what happens when the fluctuations are not weak? So that was the question and the motivation for Tatarskii to get into this, and then see how do I treat strong fluctuations. Which means that if the fluctuation is not weak, how do I extend the theory to cases where the fluctuations are not weak? There are two theories that he developed. The first one is based on in the Helmholtz equation framework, and the second one is on the parabolic equation framework. The main idea here is that when you do the perturbation approach, we have an infinite series perturbation series, and normally in the weak fluctuations we restrict attention only to the first term. In the strong fluctuations, what do we do here is in that we use a renormalization theory, which what it does is that it does partial summation of an infinite series, and that in that way we can take into account higher order terms as well. And that is what allows us to expand the scope of weak fluctuations. And in the parabolic case, this is a different equation, and the approaches it's quite different. The main, here we use a different technique where the Markov approximation. The Markov approximation allows us to treat the correlation as a delta function, and this allows us to obtain closed equations for all moments of this problem. Although we obtain closed equations for all moments, only the first two moments we can have an exact solution. The higher order moments are out of reach for at least at present. It's out of reach of any analytical. It's very intractable. So this is with these are the tools that has been extensively used in many applications. If you see that there will be in all these applications, I think I can list a long list in acoustics, in optics, in seismology, in remote sensing, in medical imaging, and ionosphere, as Animesh just mentioned. In the ionosphere is very much used. One of these theories are used for studying the and subsurface as well, and then ionospheric sounding, for instance. So these are the techniques that extensively used over the years. But there is a new theoretical approach for this problem that developed very recently, and it is based on stochastic asymptotics, and it's still under development. And we have this allows us to revisit the old classical approaches to this problem, and from a different standpoint. And this gives us a a different understanding, a new perspective of the things, and also it answers some of the unanswered questions that we had, because this problem, since there are many different approaches with limited domain of applications, there are numerous open questions and unsolved problems in this field. And hopefully this new approach throws light on some of them, not all, but the scope is enormous for future generation to indulge in this. So this is the main message that I want to convey in this talk, that there is a lot of details in this, and that can be very it's not possible for us to, in this short talk, to go into details, but I think this is the essential message that I want to convey in this talk. And Tatarskii has been the leader in laying out most of the groundwork in this problem, especially the strong fluctuation theory. And that's his. And even today, this is the benchmark that we have. And in spite of the fact there's enormous amount of work in recent years, none of them has made any substantial progress beyond what he has laid over the years. So with that introduction, let me get into some of the details here. Hopefully I don't, this can be intimidating to some of people because of the details, but this is, without them, I mean, I want to give a flavor of what is involved here. That's all. I don't want to, my intent is not to dwell on the details and then carry you through all the details. All I will do is to show them and point to you to certain salient features in them. That's all. With that, let me get into the talk here. So this is the geometrical optics approach. As I mentioned, this is the case when um, the wavelength is much smaller than the scale of fluctuation. This is a scale of this is a permittivity fluctuation. The scale is much smaller than the wavelength is much smaller than the scale. This means that we have only forward propagation. So we use these ansatz, and in this Helmholtz equation, and we obtained these two equations for the phase and amplitude. This is A is the amplitude and phi is the phase. So we have these two equations, and we use a perturbation expansion for this phase and amplitude, and we have this following equation for the phase. The first order phase term is given by a very simple expression here in terms of permittivity fluctuations. We can use this to calculate the covariance function for the phase and amplitude. And as you can see, the covariance function, the variance of covariance function is simply related to the spectral density. It's just shown here, spectral density of fluctuations. And similarly, the amplitude covariance is related also to the spectral density of the fluctuations. The validity, as you can see, that the validity domain is that the KL should be very small. The KL is the correlation length of the fluctuations, and this is the restriction. This is the this inequality here places restriction. L is the domain length where this theory is valid, and this is a serious restriction because in order to use geometrical optics, we should ignore diffraction. So which means that we should stay before the diffraction sets in. That's the restriction that we have for L. So the next question is, what if I want to have, expand beyond the diffraction limit? One of the techniques, the classical techniques, is the radiative transport theory. As I said, this is a theory entirely based on conservation of radiance. The I is the fundamental quantity is I, which is a radiance, and this equation, all it tells you is the energy is the radiance is conserved. So what it does is that this cartoon here shows the propagation of the radiance. S is the direction of propagation. As it propagates to an inhomogeneous medium, it gets scattered, and then so it loses its radiance as it passes on. Then that is captured by the extinction coefficient here. And because of this multiple scattering, there can be some additional radiance entering into this path from other parts of the, within this propagation medium. And that is captured by the phase function. So this is essentially an equation for the conservation of radiance. That's all it has. And the main drawback for this is that this is entirely there is no information of phase information here. That's that's the main drawback of this. So the technique that we have, if you want to take into account both amplitude and phase and stay away from the geometrical optics regime, that means that we need to place restriction on the permittivity fluctuations. So which means that I'm going to restrict the amplitude of permittivity fluctuations is small, and seek a perturbation solution for this. So we have this is a Helmholtz equation framework that we have, and we translate using the Green's function for this problem. We translate this into an integral equation for the wave function, and then this is the approximation that I have. This is what is called the Born approximation, which means that I restrict attention only to the first term in the perturbation series. And this is a simple expression for for the first term. If only this can be explicitly calculated, so I can calculate the variance. My interest, as I mentioned before, is in the first and second moment of the wave function only. So that's all I have. I've reduced the scope of the problem. That is what I want to calculate and understand. What is the behavior of the first two moments of the wave function? That is what I have done here. And the first moment, the variance of the first moment is given is directly related to the spectral density of fluctuation. This is a key result that we have, and that has been, that people in the user community well knows. I mean, if I know the spectral density and the far field is pattern is related to the spectral density of the fluctuation, this is something that is known. So what if I mean, as I mentioned, restricting attention to the first term, narrows down our scope. There's only a few problems that we can study where there is weak fluctuations. There's a wide range of problems where you have strong fluctuations. How to deal with it? I think that's a question. It's a difficult problem, and I will go you some details. There's a lot of details in this, but I don't mean to intimidate you, but let me just show you some details here. What is involved? So we start with this with this integral equation formulation of the Helmholtz equation. So this is the equation that we have, and what I'll do here is I'm going to use a diagrammatic technique to handle this problem. So as I mentioned, if you use perturbation theory, we'll have an infinite series. And, I cannot restrict attention only to the first term, and I want to take into account higher order terms. And that is what I'm going to do in a diagrammatic fashion. And this diagram helps me to do that. The wiggle lines tells you, this is the representation of the wave function. And the straight line is the Green's function representation, and the epsilon is given by this dot. So this is the integral this is the diagram form of this integral equation. And this is the perturbation series. I mean, expand this, and this line is the perturbation series that I've obtained here. I do averaging, and once I do the averaging, this curved line are correlation functions, and that is what represented diagrammatically here. I introduce the mass operator. I mean, the question is, how do I sum this? I mean, that's a big question that I have. I mean, this is a infinite series. How do I sum this? I mean, I don't want to restrict attention to the first term. That is what this Born approximation gave me. How do I take into account higher order terms? To do that, I introduce a mass operator, as shown here, which is the sum of all connected diagrams, strongly connected graphs. What I mean by strongly connected graphs is you cannot be broken up, without breaking this. If I break into two, I'm going to break some of them, I'm going to cut into this. I mean, which I cannot do it. So those are the graphs that cannot be broken. For instance, this graph can be broken. I can break it here, and without breaking the correlation structure. So that is what is the difference between strongly connected and weakly connected graphs. This is a this is the sum of all strongly connected graphs. With this, I can represent the mass operator in this form, and a Dyson equation, which is the mean equation, in a very compactly, using the mass operator representation, I can use, and I represent it in a very compact form that takes into account all multiple scattering. Okay. We can follow a similar diagrammatic technique to do the second moment of this problem. This is the Dyson equation in explicit form is given here. Okay. I can follow a similar approach to do the second moment, which is the coherence function. And this is what the coherent second order moment for the wave function. And the second line here shows the complex conjugate of this. So the second term. So this is the diagrammatic representation of this equation. And I'm going to take the average. Now, when I do the average, this is the coherence function. This is the diagrammatic form, representation of the coherence function. And these are all correlations. The lines that is connecting the dots are correlation functions. Again, as before, this is an infinite series. And I need to sum this up. And the way to sum this up is to introduce an intensity operator, which is sum of all strongly connected graphs as in the past. And I'm able to obtain a closed equation for this coherence function, which is called the beta salpeter equation, in terms of the intensity operator. So this is so we have, formally we have derived equations for the first two moments of the wave functions. However, this is just a formal expression because the intensity operator and the mass operators are infinite series. And in order to make progress, I have to make some approximations to this. And that means that I have to restrict my attention to the first term of the mass operators and the intensity operator. That's what I will do. And again, here, this is the analytical representation of the beta salpeter equation. And the leading approximation for the mass operator is the Bourret approximation. That's what it's called, which means that this only means that I restrict attention to the first term of the mass operator. And the latter approximation is the approximation for the intensity operator. Again, here, only the first term is kept here. So if I do this, the very interesting thing about this is that once I make this kind of first order approximation, I can connect directly to the radiative transport equation, because the radiative transport equation, as I tell you, is a phenomenological theory. There is no theory, no wave theory behind it, no statistics behind it. It's purely based on phenomenology. But following this approach, I'm able to connect and derive the rigorous wave approach to the radiative transfer theory. That's what I will do. And how to transition to the radiative transport equation. There is a series of steps here, which I won't go into details, but the main step is the introduction of the Wigner transform. What the Wigner transform does is that it relates, or it connects the coherence function to the radiance of this. So this is what this is, a relation between the coherence function and this is radiance. This is proportional to radiance. I'll show you what. And so I have an integral equations for the radiance function u, and I will use a approximation for the radiance function. As it stands, it's complicated. We cannot solve this. This equation is complicated for any kind of further development. So what I would do is I will make a perturbation or a approximation for u, and I will keep my attention only to the first term, u0. And in terms of the u0 is very much related. An integral equation of u0 results from this. I mean, once I make this as a closed integral equation for u0. And this expression shows how u0 is connected to the radiance intensity, which is a fundamental quantity in radiative transport equation. So then we arrive at the familiar radiative transport equation. The main difference is that we have explicit expressions for the phase function and the um, and the extinction coefficient in terms of the fundamental parameters of this problem. Recall in the phenomenologic theory, these quantities are measured quantities. They didn't have any idea what how it is related to the parameters, but now we have explicit expressions thanks to the wave approach that we used, and we have explicit expression for eta and phi in terms of spectral densities. And there are some valid, I mean, again, there are some conditions where this is applicable, and this is a condition that I have obtained. So another big advantage and a big takeover from what we went through all the this procedure is that even though we derived the familiar radiative transport equation from a rigorous standpoint, we were able to obtain validity conditions for the radiative transport equation, very clear validity conditions, because earlier people used radiative transport. They have some intuitive understanding of this. They didn't have precise validity conditions for this. Here, in this rigorous approach that we followed, we have very explicit validity conditions that we have obtained here. And this condition is only for the case. I mean, I was able to get validity condition only for the case when KL is very small. But this doesn't mean that this radiative transport equation that we obtain is only valid for this condition. But these conditions, the rest of this condition is only valid when KL is small. That is only the case that I was able to get this explicit expressions. There are other cases that needs to be explored. We don't have any tractable information as of now. Okay, so this is so far I have done. This is the Helmholtz equation framework that I did this for the weak fluctuations and strong fluctuations. But a similar approach can be done for the parabolic equation framework as well. This is what I'm going to do next. So in the parabolic equation approach, this is a parabolic equation that I start with. First, I will restrict attention to weak fluctuations, meaning that I'm going to use assume that the fluctuations are small and restrict my attention to the leading term. That's what I'm going to do. But here the techniques are different. It's not the same as it in the Helmholtz equation. Here we use a different framework. Remember that I had to do so. I have to. My interest is to obtain the first and second moment of the wave functions, and in order to do that, the main complication is this term. This term has got a product of a fluctuating part and the wave function. Once this taking average of this is a complication. So to avoid this complication, and this is a technique. This is a technique that has been developed here. It's a very ingenious technique. So we use this transformation that we for u, and once you substitute this, it eliminates this kind of product here. Just look at here. This one that this product term is gone here. This is just now the fluctuations appear as an additive term. So this is a simplification that this transformation has enabled us to do it. And now I'll seek a perturbation series expansion for this for C, and I will restrict attention to the first term, the order epsilon. That what it means is that I need to restrict attention. This is the restriction that I have. This is a condition that I need to satisfy in order to restrict my attention to only the first term. And if you take a look at this condition, this condition also places restriction on the range that I can study, but this is a much broader range than what we were able to obtain in the geometrical optics. This is a much more wider domain of applicability than what we were able to do in the geometrical optics condition. So this is definitely a substantial improvement from there. So, but the advantage here is that again, this is a very simple expression for us. I think this is the first, the fluctuation term of C1 is a very simple expression, and I can study both the phase and amplitude. That is what I'm going to do here. The phase coherence function and the amplitude coherence function can be studied from this. The phase coherence function has got this very simple expression here in terms of correlation function. And the amplitude correlation function also has a similar simple expression. And here and then in this criteria, there is an important criteria called rate of variance, which is something that I would like to draw attention to. This quantity that I have shown here is um, as shown here is sigma r squared, which is this is a variance of intensity. That's what it is. It's a photon moment quantity, and it turns out this is the expression that I have for the variance of the rate of variance. And this expression is of special significance. What I would say is that the rate of variance is a function of Cn square is just the our variance of permittivity. Okay, I mean in the atmospheric context people use Cn square, but it is the same as sigma square, or the variance of permittivity that is used here, and the K and L. So the sigma r square is a function of both the variance K and L. So the sigma r less than 1 is the small fluctuation regime. So the small fluctuation, you shouldn't think that small fluctuations mean regime means it's only small variance fluctuations. There are other factors also involved. The K and L also is involved. I think this is an important thing that I want to draw your attention to, because it requires some thinking to understand this, because you have to let this sink in your head. How this small fluctuations mean, how the K. I mean, it took me a while to understand this, because initially when I started working on this, I always used to think that small fluctuations mean the permittivity must be small, but no. There are K, and the range and the wavelength is also the range. Especially the range has got an important domain, important role in playing this. So I wanted. I mean, this is a good point, good stage that I want to keep. Point out this, because this is the domain that we have studied so far. Okay, the sigma r square less than 1. That's the domain. That which is weak fluctuation regime. But there is a substantial um, area which falls into large fluctuations. Um, I'll give you another example for you to understand what I mean by large fluctuation. Large fluctuation does not mean that Cn square or the variance should be large. If I increase the range, then also you get large fluctuation. If I increase L, then sigma r squared becomes large. So we also run into large fluctuation regime just by increasing the range. That's what we encounter in practice. So we are interested in long range propagation, and how the how the wave function behaves because of fluctuations in the medium. That's what that's the strong fluctuation regime. So in the again in the strong fluctuation regime, in the case of the parabolic equation framework, is not the same. It's very different. I mean, we don't the techniques and the approaches are very different. Here, what we employ is a Markov approximation. It's a very key approximation that we employ in order to. The other approximation that I've listed here are not that restrictive, but the Markov approximation is there. Let me just say what is Markov approximation. Markov approximation technically is much more detailed, but for our purposes, I'll just point out one thing here. In this problem, Z is the propagation direction. So what the Markov approximation means is that we have a delta correlation function in the propagation, along the propagation direction. That's what it means. Okay. And there is, I mean, this is not an arbitrary approximation. There is some, there is rigorous ground for making this, which I won't be able to do this in this talk, but just take my word, and they say that this is the approximation that we will need to make. This is a delta function correlation approximation along the propagation direction. But we keep the correlation in the transverse direction as it is. So we don't do anything with that. This enables us to derive closed equations for the moments of the wave functions of all orders. So to do that, first we write the product of wave functions. I mean, there is some series of steps that is involved. because of the fact I will be able to derive moments of all orders of moments of wave functions. I'm just listed I've become I've taken a general step of all product functions here, and then we take the moments here, and then a key step in analyzing the moment is the Fruitsu-Novikov theorem. And the Fruitsu-Novikov theorem enables us to evaluate this product function here in terms of correlation function. B is a correlation function in the transverse direction, correlation function of the permittivity fluctuation. And this allows us to obtain moment equations, closed moment equations for all orders. Okay, this is very surprising, and this is as far as anybody could have hoped for, because in the Helmholtz equation framework, we were able to get closed equations only for the first two moments. The outside, the higher order moments were beyond reach. But whereas here in the parabolic equation framework, we are able to obtain closed equations for moments of all orders. So this is a significant development, and that's the that's the advantage of parabolic equation framework. Although it is a subset of the general Helmholtz equation framework, because the parabolic equation framework only works for in the high frequency domain. So in spite of that, the progress that we can make within this framework is enormous. Although we were able to obtain closed equation for moments of all orders, only the first two moments we have exact solutions. Only recently we were able to get solution for the fourth moment by making some approximations, further approximations, not exact solution, but even that is a recent work that that was that's the progress that we have made. All our higher order terms are beyond reach, intractable at present. So now I think let me just point out something. I mean, Tatarskii went ahead and did some within this framework. He also derived a closed equation for the characteristic function, which is much more complicated, which is I won't go into that. So as I mentioned earlier, I've listed a long assortment of techniques that is used for analyzing propagation in inhomogeneous and turbulent media, and each one has some restrictions, and there are some validity domains that is placed on it. Each one, when you use some of these techniques, you should be aware what is the domain of applicability, and so it only works in this. And unfortunately, applications are agnostic to all these kinds of restrictions. So how to deal with that? So there are many open questions and problems here. Before I go there, I think I'll just want to say a recent development here, which adds to the theoretical tool set that we have, is the scale separated asymptotics, which is essentially a stochastic asymptotics. Here, the scales are very important. I mean, we have to be very careful about, there are different scales involved. I think one of the scales is that, this is the correlation length, and this is the regime length, L, the capital. I think what is the regime that we want to study? And epsilon is a small quantity that much less than one, which is what we'll use as a scale for, what is small and what is large. And what we are interested here, I think I'm going to use this for a special case. I'm going to use this stochastic asymptotics for a particular very special case, just to illustrate what is involved and what can be obtained from this. Again, I'm going to take this example of the Helmholtz equation framework. And my interest is in the long range behavior of this wave function. Okay, so which means that I want to make this transformation where epsilon is a small quantity, which means that I'm going to treat the long range behavior. That's what I want to study. I mean, what is the moment functions for long ranges? That's the question that I have. And when you say long ranges, the range is much larger than the wavelength. and much larger than the scale of fluctuations as well. And the appropriate scale for me is that I also want to treat this the fluctuations v of the order of square root of epsilon. This is only the this will mean that, why I'm doing this scale. I mean, there's a lot of details involved, and there is the rationale for choosing this. There is a lot of detail. I think I won't go into the details here. I'm going to present this in talk coming up in January, and also in in the international IEEE antennas and propagation meeting as well. And this is going to be one of the papers that's coming up there. So I think this is the appropriate, just take my word, and then this is the appropriate scale, but there is some reason why I chose this. So if I do this, then I have an equation for the scaled wave function psi epsilon that shows here. And I will use the Wigner distribution. As I mentioned, the Wigner distribution is used for connecting wave functions to radiance function. And so when I use this, I end up with here, and the leading term of the Wigner distribution satisfies the same radiative transport equation as I obtained earlier in the phenomenological. So another approach to obtain the radiative transfer equation from a totally different approach. I mean, totally different framework, totally different list of approximations involved. So this is this has added to the list of understanding of how the radiative transfer equation behave, where it is, what is its origins, what are the foundations in which it's built on, and what are the restrictions, and what are the domain of applicability. All those things we have a much better understanding thanks to this new approach. So the new approach, I mean, it's a good the new approach. Any time a new approach comes, it is a good opportunity for us to revisit some of the old classical techniques and see how do we understand, what are these, can we understand some of the open questions that we have. So this is a work in progress. So there are many open questions, and and areas which has not been studied so far in this domain. So so people who want to get into this, the field is wide open. I think I would say, in spite of the giant strides that Tatarskii has made, there's a lot of open questions and opportunities for further development. So I think I'll want to end this presentation by mentioning, Tatarskii was a leading pioneer, unmatched in this. So I think the rationale that he used for this, I mean, he didn't have all the tools um, that we have today and all the understanding that we have. I mean, his rationale was more on the physics-based intuition that he used to derive some of his strong fluctuation theories and for studying this problem. But we have all the theoretical tools, the advancement that was been made in the theoretical domain that we have, and we can take a much more rigorous approach than what Tatarskii was able to do. But having done all those things, uh, we get a better understanding. All the things that he has done based on physical intuition falls right there with all the more rigorous domain here. So he had, it's very amazing. I was fortunate to have known him, met him several times, and had discussions with him. So it's very privileged that to even to share that with you. Um, so that's the legacy that he has left behind, and onto future generation. That's Thank you for your attention. That's all I have. I mean, I'll be happy to answer questions. And before I end, I want to make a comment. I think I'm organizing another pioneer in this field. I think I mentioned about Tatarskii and his legacy. Another pioneer in this field is Professor Ishimaru. Okay, Well, Tatarskii has laid all the theoretical framework and for the basic theoretical framework. It was Professor Ishimaru who took that and brought in a host of applications which covers everything. I mean, the variety of applications that I mentioned in acoustics, optics, medical imaging, ionosphere, plasma physics, medical imaging, remote sensing. He took that everywhere and applied. I mean, his scope of where he applied is enormous. And he took that and then see how that the essential basic theory is applicable in all parts of science and engineering. So that's what he has done. So I'm organizing a special tribute session for him at the IEEE International Symposium for Antennas and Propagation that's going to take place in Portland, Oregon. And here's my contact information here. And this is the website for this. And the deadline for submission for abstracts is in 27 January. We have a month's time for us to participate. I welcome all of you to participate in this. And there is also for students, for those of students, there's a student paper competition as well. And it has its own, the format and guidelines for that is also listed in this link here.
Website.
I'm sorry.
Website.
Yeah, this is a website. It's a web link. The web link for the conference, and where you can see all the details about this special session and also the deadlines and submissions, everything. So with that, I'll conclude this talk, and I'll be happy to take any comments, suggestions um, from you. Thank you very much.
Thank you.
Thank you very much, Dr. Saba Mudaliar. I think you've given a very comprehensive description of scattering phenomenon in turbulent media. I mean, what I understand is basically what you're saying is the treatment goes as the fluctuations are in permittivity, and you have different treatments depending on the scale of the permittivity fluctuations, as compared with the wavelength of the wave that is being scattered, and depending on the different situations, you have different kinds of treatments. You have Helmholtz equations or parabolic equations, and you've also talked about weak and strong fluctuations. In fact, you've given a very wide range of treatments,
Yes.
and have described domains of applicability of each one of these. So I think it's for somebody who's planning to start work in this area, particularly the younger people, it'll be a really nice kind of resource material, information. And I'm sure there'll be, some of our colleagues, some of our young students that would eventually want to get in touch with you if they want to, make some interesting progress in this field. I'm sure some of our colleagues here will have questions, but first of all, I mean, I have the prerogative of asking you my own very naive question. I don't know whether it's very naive or stupid, but please pardon me if it is. Um, what I could understand is you were actually describing a wave propagating in the forward direction, in the z direction, and then the scattering manifested itself in the form of an extinction coefficient, right?
Yes.
Okay, so as an experimental physicist, what in addition to the extinction coefficient, I'd also be interested in the backscatter or scattering in a particular azimuth. So in all these equations, I didn't find a term which had an azimuthal dependence.
Yep. Okay. I think, can I go back to my slides? I think I can show you better.
Yeah.
Okay.
Yes.
You see my slides here?
Yeah.
Yeah,
You,
we
Okay.
are
All right.
seeing,
So
we are seeing.
maybe you'd like to go back to the, no, this is
yeah,
fine.
yeah, I think I'll just go here. Okay.
Okay.
So I gave you initially a start. I mean, I think it's good to um, okay. So I think I'll go say. I think hold on. I mean, this is just loading, so I think it takes my time. Some
Okay.
Uh-huh.
yeah, it takes
Yeah,
I mean okay, all right. It takes time to wake up. Okay.
yes. It is, I told you. Yeah, maybe we shouldn't ask him to go back and forth, given
No, I
the.
think I think okay, all right. So before I go there, I think I gave you two frameworks. The Helmholtz equation framework and the parabolic equation framework. Okay.
Yes, yes,
Yeah, to answer Dr. Sengupta's question is that these two frameworks, in the it is the parabolic equation frameworks that treats the forward scattering only. Okay. So the Helmholtz equation framework, it has no restriction on the direction, on azimuth or everything. Back scattering, forward scattering, everything is involved. I think let me show you some. Um, okay, so that's the I think if you look back, I think in the just a quick question before, I mean, this it takes time for me to load that page, but to answer your question, no, there is no restriction as to the direction. I mean, if you only in the parabolic equation framework, it is only forward direction. It's a forward propagation direction. But you restrict that, but then you gain a lot. I think, which means that when you use the parabolic equation, you get closed equation for moment of all order moments of wave function. So that's a that's you pay a small price in terms of restricting yourself to forward propagation, but then the advantage that you gain is that you can get um, equations for moments of all in all orders. But if you're interested in the backscattering, the Helmholtz equation framework is what you should use, and that includes scattering in all directions, including backscattering.
Okay, great. Thank you. Maybe I need to go back on your slides later on.
Yeah, I mean half of my talk is on Helmholtz equation, and it definitely that is it is not. I mean it's not restricted to forward scattering only, and the extinction coefficient. Okay, talking about extinction, it's good to take let me take the picture that I have for. Um, yeah, now you see the
Given
picture
the,
here. You
Yeah.
see the picture. Okay,
yeah,
this picture gives you what it means is that okay. So we have we have the wave the wave propagating in this direction, S direction, and because of this medium is the medium that is that is going in the cylinder is an inhomogeneous medium that scatters, absorbs, and emits and all that. So what is going to when the wave propagates, it is going to lose its because of scattering, it's going to lose its radiance, and that is quantified by this extinction. Okay,
Right.
and the extinction is a quantity, but it goes there. But then this can scatter in all directions because the medium is homogeneous. It can scatter in all directions. I think I just showed if it goes in this direction, but it can scatter in all directions. So it is not restricted to forward direction only. Um, I think the Helmholtz equation framework, I think it has got all right. It is not, there's no restriction on the direction of propagation. In fact, the radiative transport theory has been used for satellite remote sensing. So, what do you mean by satellite remote sensing? Of extensively used for it, for land cover, for soil moisture. I mean, recent program NASA is doing a recent program, satellite campaign, where they want to map soil moisture content in and the deforestation. That's another program that they have. So there's a whole range of remote sensing programs that NASA is conducting, all of them using this kind of techniques. And yeah, I think so. So remote sensing from satellite without backscattering, it's not possible. So
Right. Great.
Oh,
Well,
yes.
thank you very
Okay.
much.
Okay.
Anybody else?
Yeah.
Prasanna, you have a question?
Yeah. Yeah. So you talked of, I have again only naive questions. You talked of epsilon being the fluctuations in permittivity, right?
yes.
So throughout, you have not changed that, because you kept saying that the fluctuation sensitivity is very small. Fluctuation of permittivity is very small.
Yep.
Yeah, because permittivity constant itself is very small anyway.
Mm-hmm.
Yeah, so that is very clear. The other term which I was trying to understand was this CN squared term, which is,
Yeah.
I suppose
Yep.
it is a standard that probability density function or whatever we
No. I
call.
think
And
CN square. I think
Mhm.
if you are in the, I think it's more in the optical sciences community
the,
that's
the
used.
optical, okay, in the optical, CN squared is the structure function.
Yeah, exactly.
Okay, so you are referring to that same structure function,
Yeah, the structure function. I mean, CN
which
square
we,
is synonymous with the variance of permittivity. That's synonymous.
yeah, okay,
I mean,
variance.
that is, in that
Yeah.
community they use that CN square as, that
Yes,
terminology
yes,
is
yes, yes.
used. But
That's right. That's right.
you know, this is this the fundamental theory is applicable to a whole host of different problems where, I mean, who may not know
Yeah.
anything about CN square. I think it's only the optical sciences.
Yeah, right.
I think
Okay.
the atmospheric sciences people, they are the people who are, I mean, for them, CN square is their bread and
Yes.
butter.
Yeah, that's correct. Yeah, they use that. Yes. And similarly, the extinction coefficient, which is used
Yes. Mhm.
extensively in the atmosphere,
Yeah,
atmospheric
exactly.
extinctions and whatnot.
Yes. Extinction
Okay.
coefficient is used
Okay.
there. Yeah, I think that some of these terminologies are, um, you know, it appears in one context, and
Yes.
it appears in the. I mean, especially there's one of the things that I, if you navigate through the literature in different science and disciplines,
Correct.
you
Correct.
need to have a translation table.
Glossary
Yeah,
of terms.
exactly. What it means here and what it means there, and to read
Yes.
those. I mean,
Yes. Yes. Yes.
to read those papers.
That's right.
Those terminologies you should be familiar. Otherwise,
Yeah,
what does
yeah,
that
yeah.
mean here? I mean, there is a translation that is required.
That's very correct. That's very correct. We face that even between dealing with the optical things and radio things.
Yes,
We face
exactly.
that, although they mean the same thing. When you go to the what is that, Born and Wolf textbook, it is all the same.
Yeah, but when you go to acoustics people and then seismology
Yes.
people, they their terminology is very different. So
Yeah. Right. Okay. Okay. Yeah. Your talk is very enjoyable, except that it starts going out of our head after some time.
well, I think I
you
didn't
know,
I think
for
it's a
example,
yeah, it is a I just want to give a flavor of what is involved.
yeah, yeah,
That's why I
you
think
can
in the
see.
initially I spent a substantial 5-10
Yes.
minutes just on the introduction slide to give
Yeah,
you
yeah,
an
yeah,
overview,
yeah, yeah. In
so
fact,
that
I was not
I don't
familiar
lose.
with. Yeah, I was not familiar with the Feynman diagrammatic representation of the correlation, cross
Yeah,
correlation.
those are,
That,
very specialized
that
things. I mean, this can
yes,
become, I think this can become really, I think I can tell you this, this is at the forefront of research. Why, I
yes,
think, you know, the partial the stochastic partial differential equations is still
yes.
at its infancy. Okay, because what I
Ah,
mean,
yes,
the reason why we don't have, I mean, we have these approximations, very
yeah,
different approximations. I think we just make this approximation here, that approximation here. Each approximation is only valid within a small range, and
yes,
often in the
yes,
user community, people are not aware of what ranges are there. I mean, and the ranges itself,
yes,
when a theory is described, like for instance, radiative transfer theory, right now we are seeing
yes,
here, it has
yes,
been used in the, successfully for in many applications, but
right.
have not found anybody who placed exact definition of the that describes the domain. I mean, domain meaning I want to have a parameter domain. Okay, if I use this parameter, what is the parameter
Mhm.
domain that I have to stay within in order to confidently use this theory? That's the question. That has not been
Yes,
defined
yes.
at all. And
Okay, okay.
people loosely, I think that in the application community, people loosely think that, okay, all right, this is good, and or I use I use this, and I was able to get good agreement with measurements, and so this theory has worked well.
Yes.
So that's
Oh, yes.
that's where. So I think those things are not well defined. The primary reason for those things is because the stochastic partial differential equation is still at its infancy, and people
Mm,
are even there. They are making the only small progress is going there. Unlike the traditional partial differential equation is much more advanced. The stochastic case is um, the you know there is rigorous theory, but only for under certain very strict conditions. The Markov approximation has
mm,
been widely used in the community for that, and there are many issues here. I think primarily because when you go to stochastics, there are many fundamental issues. For instance,
mhm.
talk about convergence. I mean, we in the calculus we know about convergence. There's an absolute convergence, weak convergence, and term-wise conversion. Or in the when you go to stochastics, there's only one. I mean, in absolute convergence gives it in the real world community. The absolute convergence gives you, but when you go to stochastic, there is a whole host of convergence issues. How does what do you mean by convergence? There is a probability. There is a
Yeah.
convergence in probability. There is convergence in mean square, and there is
Mhm.
convergence in different moments. Like for instance, the convergence in first moment. The criteria for convergence in first moment has no correspondence to convergence in second moment, because second moment gives you
Mm,
it's a totally different. So there are
mm,
many issues, open issues are there, and that
mm.
has that's an active area of research. So we don't have so I think
Wonderful.
that is one of the reasons why we have limited. I mean, the applications, I mean, where we encounter this is enormous. I mean, wherever, I mean, it's not going to go
Mm,
away at all. This topic is going to
yes.
remain as long as there is nature. Okay, we will have this.
Yes.
But but
This looks like a wonderful area of research for PhD students in India, because many of them do theoretical framework solutions. So it should be widely propagated in India in the sense that encouragement to students to work on these issues. As you say, the field is still open. It's a lot of work, good work, which can be done.
yeah, but I think the more, I
That's
mean,
great.
people are faced with a pressing issue. I mean, they need to have solved this problem today. Okay, and they don't have time for.
Yeah.
And
Okay.
so the need is that we use whatever techniques available and then proceed.
Right. Right.
Okay,
Right. Right.
NASA or ISRO goes and collects the data, and they want to
Yeah.
analyze this whatever tools they have. I mean, they don't have the time
Yeah.
to.
Yeah. Yeah.
So
Time.
so
Yes.
that's the situation everybody faces. So
Yeah.
yeah,
Okay.
only rarely people come out like Tatarskii and then break grounds.
Yeah. Right. Okay.
Great.
Thank you.
So, are there other questions or comments? Animesh, you have any
Yes,
comments?
can you hear me?
Yeah, very
Yes,
well.
yes,
Thank you.
Okay,
Yes.
okay. It was a very nice talk, holistic approach. And in fact, I got interested, particularly in the aspect of strong scattering and weak scattering. You know that there is a lot
Mm,
of application of your theories in our area. For
yeah.
example, radio propagation through raining medium. It is an
Uh-huh.
ideal random
Yes.
medium,
Yes.
and a lot of works have been done,
Yes.
and a lot of works have done to predict attenuation as well as depolarization.
Yeah.
And people usually used single scattering theorem,
Yes.
single
Hmm.
scattering approach, but that is much easier. I think
Yes.
this corresponds to your weak scattering regime in your case.
Yeah. Right.
And the strong scattering or multiple scattering, which is more
Mm,
commonly used in our area.
yeah.
Now, what happens that multiple scattering or strong scattering formulation that have not yielded very good result. That means when we compare our actual experimental measurements with
Hmm.
all this single scattering and multiple scattering, it is
Yeah.
found that single scattering is closer to experimental measurements
Hmm.
rather than your multiple scattering.
Yes.
So one possible reason could be that we could not specify accurately the propagation medium in terms of
Hmm.
gas size distribution, all these things. But is there any inherent issue with strong scattering formulation that prevents to be more uh, accurate to predict experimental data?
I'm surprised to hear that because the strong scattering and weak scattering are not exclusive. Strong scattering,
Yeah,
the strong fluctuation theory um, includes weak fluctuation as a special
right,
case.
right,
So
right,
it
right,
shouldn't be
uh,
these are not disjoint sets.
right.
It includes that. So I'm surprised to hear discrepancy. I mean, if you get some agreement with your um, uh, if your weak fluctuation theory matches
Yeah,
with your experiment better,
yes.
uh, th-
For
then
example,
yes,
for
yes.
example, say there is an ITR model. You must be aware of that. ITR
I'm sorry.
model for ITUR,
Okay.
International Telecommunication Union radio climatology model. They
Uh-huh.
models for attenuation, phase change, depolarizations, all those things. And their
Okay.
model is based on experimental data
Okay.
all over the world. So
Hmm.
ITR model is closer to single scattering calculation rather than multiple scattering. Multiple
Uh-huh.
scattering actually underestimate. Whenever
Uh-huh.
you have the
Hmm.
same kind of specification,
Hmm.
multiple scattering gives you lower value of attenuation compared to single scattering, right? Now,
Yeah.
I presume, just let me finish my comment, multiple scattering require more accurate description of the random media rather than single scattering. That's why if there is any error, any inaccuracy in considering the random media for multiple scattering, it has to be pretty accurate. Otherwise, it will give not accurate result as desired. Okay, this is my comment, and I want to answer any
Okay.
response from you.
Okay. I think I have I have a I have I understand what your question is. I think this is an issue. I think people using it. I think the what you mean by attenuation is you're taking um, you know the the attenuation that resulted from multiple scattering and then using it in your
Scattering, yes.
proper propagation problem.
Mm.
That is that requires some care. I'll tell you why. Because um, that extinction that is obtained from multiple scattering theory has got a range restriction where we have to use. I mean, only it appears only in the at a short range. That's where it has to be. I mean, which means that, I mean, not attenuation, like for instance any kind of modifications to your propagation constant that you obtain from multiple scattering is only for a limited range. So what you're doing is that you are you are you are getting an effective propagation constant by using multiple scattering theory, and that has a limited range where it appears. Okay, and then if you're using it in a longer range beyond that, then that is something artificial. I mean, this not
Okay.
it doesn't. I
Okay.
mean, the theory doesn't say that. You're artificially extending the 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 effective attenuation, which is supposed to be used in a short range, to an extended domain. I mean, that will go to infinity. That'll vanish. I mean, in fact, I mean, so that cannot be. That may not be. That's one. That's one comment that I want to make. Another comment is that what kind of the statistical analysis starts with the model, and then what that model. I mean, this is a model, and how that model closely relates to what we have in reality. That's a big problem. I mean,
Yeah. Yes.
this is what is called. I mean, this is for everybody, for in all branches of science. Is that in nature? Nature doesn't come up with model. You model it, and then what does that model has to do with what we see in nature? Which
That's
means, what
true.
is the ground truth? You take a, people. It's easy to fly satellites and collect data, but then what is the ground truth? I mean, if I use some model, what is the ground truth that we have for the for the data that we have? So I mean, that is very limited. And even if we have if we can do some measurements, and then how to relate that measurement to the model parameters. I mean, that's, these are all difficult questions. I mean, this is not, there's no simple answer. I mean, theory doesn't answer all the questions. I mean, modeling is a
Oh, that's
very
true.
yeah, modeling is a substantial part of this whole exercise. I mean, the modeling doesn't come up easily. I think in nature modeling, how to model what is in nature and translate it into parameters, that has been going into this problem. It is easy for me to say spectral density or variance, but then what does that spectral density and variance has to do with what we see in nature? It's not easy to say questions. Yeah, I think
Yes.
that's a separate area of measurements and characterization and modeling. It's a separate area.
Yes. Yes. And I understand. Yes. And I understood your point. Yes. That means for multiple scattering or strong scattering, you have to get a more accurate uh, description of the propagation
Of the
medium or random
Yeah,
medium.
exactly. We have to. I mean, otherwise,
As you mentioned, that there's a range limitation, right? That means so if
yes.
so, single scattering approximation may not be sensitive to that limitation, but multiple scattering is more sensitive to that limitation. So
Well,
in that
I
sense,
think.
mhm,
I
Okay.
think I think you have to see the
yeah,
range, the domains at all. I think that's where
okay,
it is. I mean, the domain is single scattering and multiple scattering. Even it's not just the fluctuation alone. The range also is involved. I mean,
yes,
I mentioned
yes,
it. So there is a
yes,
I mean, it's a combination of things. I mean, there is no simple answer to this. I think it's a combination
okay,
of
okay,
factors: the model, the theory, and the measurement. I think we also assume that the measurement is. Um,
accurate.
yeah, accurate, and it has
That's not
been I mean, most important, I've been seeing several measurements in my career. Calibration is an important factor. I mean, how did they calibrate things? I mean, how much confidence that we have in our
true.
measured results. So that's a there are there are a lot of measured results, but then few calibrated results of high quality.
True, true. Okay. Thank you very much.
Well, thank you. I think we'll take
Yeah.
one more
Well,
question. There was a question from Dr. Banerjee.
yes,
Dr. Banerjee, please go
yeah.
ahead.
Thank you. You have a very good talk. So it is highly highly specialized subjects which I have never dealt with. So my question is related to that we often hear the scintillation problem in the signal, particularly in GPS.
Okay.
But there is not very much understanding how scintillation effect will and the ground level, how it will affect the signal and all these things. How your theory, this sort of treatment, can it help in understanding better the scintillation issues?
Yes, indeed, absolutely. I think I have not gone there. Scintillation is a fourth moment study. Okay, I have just read the first and second moments here. Scintillation involves the study of fourth moment of the wave functions, which I have not done. That it can be done. So that is what is going to give you information on scintillation. Scintillation has got many issues. I think where there's a scintillation regime is there, so we have to stay in that regime. So we have some understanding, not as thoroughly that we have, but definitely scintillation in radio signals. Is that what you're saying? I mean, radio GPS. Is that what you said?
Yeah,
What is the
I have
radio signal?
related to this. I was only wondering whether your parabolic approach will be a better thing or a Helmholtz equation approach.
For scintillation problem? Yeah, that's your
Yes, yes.
question. And that essentially depends on the wavelength and what kind of wavelength are we talking, and what is the medium that is. I mean, it's in atmosphere.
Yeah,
Yeah,
because
he is referring to atmosphere.
Yeah,
because you
if it is.
said that parabolic can handle the higher order terms.
Yeah,
So
yeah, yeah, yeah,
when you are
exactly. So
talking about the fourth moment,
yeah.
uh, so that may be helpful that you go
Oh
for a
yes,
parabolic
absolutely.
approach.
Absolutely. Only the parabolic equation has got any. I mean, has got. I mean, we can have a handle on fourth moment, and your application is the main criteria w- where parabolic equation is model is applicable is that the wavelength should be much larger than the fluctuation
Yeah,
scales.
Yeah,
Okay, so I think in the case of
that may be
applications
still
like
valid. That may
yeah,
be
it is
valid.
valid.
Hmm.
Yes. So which means that that's if you're no okay, I'm sorry, I didn't say that correctly. The wavelength should be much smaller than the fluctuations. I mean, that's where the forward way
Okay,
okay. I didn't
okay. That may
uh,
not be valid.
No,
yeah,
that is
okay.
actually that is valid because the
Is it?
wavelengths that we are talking about are in the L band. That's just about a
Yeah, but
centimeter. So,
that is few centimeters, isn't it? 20
few
centimeters.
centimeters, and these irregularities in the ionosphere, they are typically upwards of several meters and
Yes,
No, no,
exactly.
no,
Yeah.
no. But the fluctuations we are dealing with are only the fluctuations in the electron density and the permittivity,
yeah. The scale size,
right?
those fluctuations are upwards of several meters and so on.
Yep.
They
Yep.
are
Yeah, I
not
mean
in
those, I mean,
centimeter.
Okay.
yes. You're right. I think especially, yeah, you're
Correlation
right.
scales are large.
Yeah, now I understand your problem. I think in the ionosphere,
Yes,
definitely this is a good approximation.
yes.
Unless you are dealing with small irregularities, small scale irregularities of the same order of the wavelength. You may be, that is where you're not capturing. Definitely um, as Amitabha mentioned that. Um, if in the parabolic scales, parabolic equation, if you approach, you ignore backscattering. So
Hmm.
whenever the backscattering happens, when the scale size is of the same order of the wavelength, you can have backscattering. So that is where. But if you're not, if as you mentioned, there's the wavelength is of the order of 3 centimeters or 10 centimeters, and your scale size of the fluctuations are of the order of meters or tens of meters. That is typical in the, I mean, people have, I mean, ionosphere, it's very large scale. I think I've seen
Right.
hundreds of meters. I mean, those are some of the fluctuations take place in the hundreds of meters. Definitely this is. I mean, people use ray theory in this. I mean, that has been the one that has been used for a very long time. Only now they are using the wave approximation, way more accurate, wave theory and all for the ionosphere. But traditionally, people have been content with the ray approximations, just ray models, and they've been using. That's my, that's. So, I mean, I'm not a specialist in this area, but I think I've, from what I've seen in the literature, this is what I observed.
Okay, thank you.
Great. Um, are there any more questions or comments? Well, if not, may I take this opportunity on behalf of the Indian Radio Science Society, INRAS, and on behalf of all of us, thank you, Dr. Saba Mudaliar, once again for such a wonderful talk. I mean, this is you've really touched upon the subject of scattering, propagation and scattering through turbulent media in a very comprehensive manner. And since, as I mentioned to you earlier, this is being streamed live on YouTube and eventually is recorded. So the talk is archived and it's perhaps going to be of great interest to a large section of our radio scientists in India and indeed anywhere else in the world too, particularly for the young scientists amongst us. So thank you once again for taking out time to talk to us, and and we hope that since you've already given your contact details, should any one of us have any further questions or queries, we could get in touch with you. We hope you'd, be, you'd like to be contacted later too.
Yeah.
Yeah.
Thank you. Thank you very much.
Thank you.
Thanks very much. Thanks very much for the opportunity, and it was nice talking with you. It was my pleasure participating in this. Thanks all.
Thanks. Thanks.
Bye.
Okay, so thank all of us who have joined here. And with this, I am closing this meeting. Thank you all.
Thanks.
Thank
Bye-bye.
you.
Good evening and